Organizatorami Copernicus Festival, edycja Język, są Fundacja Centrum Kopernika, Fundacja Tygodnika Powszechnego, Tygodnik Powszechny oraz Uniwersytet Jagielloński. Cały projekt jest współfinansowany ze środków Miasta Krakowa. Wsparcia udzieliło też Ministerstwo Kultury i Dziedzictwa Narodowego oraz Templeton Religion Trust. Cały projekt objęty jest patronatem honorowym prezydenta Miasta Krakowa. Dziękujemy również Krakowskiemu Biuru Festiwalowemu oraz Muzeum Narodowemu w Krakowie za kolejny rok współpracy przy organizacji Copernicus Festival. Wszystkich wspierających to wydarzenie nie sposób wymienić, dlatego też oznaczenia naszych partnerów znajdą Państwo w katalogu festiwalowym. Okay, let me now switch to English and say a few words about our distinguished lecturer. So, Professor Paul Davies is a physicist, primarily, but not a usual one. After his PhD at the University College of London, he moved to Cambridge to work with Fred Hoyle, a distinguished cosmologist. And cosmology was probably the first passion of Professor Davies, and I think it still is very much. But the usual cosmology was not enough for Professor Davies. Therefore, he plunged into the misty domain of quantum field theory in curved spacetimes, which includes in particular quantum cosmology. Now, as a mathematical physicist, I can tell you that this is probably the most complex domain of mathematical physics I can think of. But still, that was not enough, and Professor Davies got interested in the origins of life, in the phenomenon of life itself. And he became probably one of the first in the world astrobiologists. So not only he is still looking for life beyond Earth and intelligent life as well, but also he's interested in the very origins of life. How did it emerge? What's its relationship with physics, with chemistry, with information theory?
Z chemią,
And more
fizyką
recently,
i teorią
Professor
informacyjną.
Davies got
Ostatnio
involved
pan
into
profesor
the
Davies także zaangażował
battle
się
against
w
the biggest enemy of
bitwę
life,
przeciw
as we know it,
największemu
which is the cancer.
wrogowi
And again,
życia, czyli
he had some
nowotworom.
revolutionary
I
ideas
miał pomysły iście
track the
rewolucyjne,
deep evolutionary
które
roots of the cancer.
są w stanie po prostu śledzić,
Currently, Professor
jak
Davies
rozwijał
is
się ewolucyjnie
Reagan's professor
nowotwór,
and director
rak.
of the Beyond
Jest
Center
dyrektorem
Arizona State
Centrum
University.
Beyond na Uniwersytecie Stanowym
Among
w
many
Arizonie.
honorable distinctions,
Wśród
he is
wielu tytułów
winner
honorowych
of the Templeton Prize
otrzymał
and a
nagrodę
member of
Templetona i
Order
jest
of
też
Australia.
członkiem Orderu
Curiously
Australii.
enough, in April
Co ciekawe,
99,
w kwietniu
an
99
called
asteroida
1992 OG
1992
was
OG
officially renamed
została
as Paul
oficjalnie
Davies.
nazwana.
to honor him. But Professor Davies finally is not only a distinguished scientist, but also a best-selling author. And his new book, which is his 31st book, tackles the information and the language of life. And this is a fascinating story. So, Professor Davies, the floor is yours.
Well, thank you, Michał, for that kind introduction. It's a pleasure to be here. I'd like to thank the Copernicus Center and Michał Heller for inviting me to this wonderful city where I'm told that sometimes the sun shines. I've yet to see it. I'm going to disconnect it so I can perhaps walk around a little bit. And let me just get all my equipment in order here. So for thousands of years, people looked up at night and watched the planets crossing the sky. And it was obvious even long ago that the motion of these planets, whilst complicated, was not random. It was systematic. But it remained a mystery until the year 1543. I don't need to tell you who this gentleman is here. And he explained the motion of the planets in terms of the sun in the middle and the planets moving around it at different speeds. But he made no attempt to connect the motion of objects in the sky with the motion of objects down here on Earth. It took a few decades before Galileo investigated the law of falling bodies and generally made a start on trying to understand what we might call earthly motion. But the link between the two remained mysterious for several more decades until Isaac Newton was able to produce a set of mathematical laws that connected the motion of objects on Earth to the motion of the planets in the sky. And therefore, at a stroke, he unified physics and astronomy, two areas of science that had previously been completely disconnected. Now, the point of this story is that today we face a very similar disconnection or schism between two fundamental branches of science. On the one hand, we have physics, which deals with particles of matter, and then we have biology, which deals with living things. We might say that biology concerns itself with living matter and physics with non-living matter. And what, of course, we would like is to have some way of unifying these two great branches of science in a single conceptual scheme. This is a very deep problem, and the reason is that life is amazing in many ways. In spite of huge advances in biology in the last few decades, nobody knows really what life is or how it began. Let me just run over some of the properties that make us feel that life stands out as something very special and very different. Living organisms seem to have some sort of inner power or agenda. They have goals and purposes. They seem to go against a fundamental law of the universe that I'm going to talk about shortly, that things tend to have a natural tendency to decay or degenerate. Life seems to go the other way. It makes order out of chaos. And it does this by self-organizing. That is, living organisms don't look to outside agencies to organize their material and energy flows. They do it themselves. They seem to evolve in an open-ended way. There seems to be no limit to the number of different biological organisms that are possible. Forms most wonderful, as Darwin referred to it. And they achieve states of the world that would seem to be impossible by any other means. And I'll just give you one simple example. For the last 4 billion years or so, there has been no plutonium on planet Earth, but just in the last few decades, suddenly there is plutonium. When the solar system was made, there was some natural plutonium from the stars, but it decays after a few million years, and so there was none until recently. Now suddenly there's plutonium. How can we explain this plutonium appearing at this time on Earth? Well, the answer is, of course, because it's a product of life. It's a product of human life, of human technology. We might think the same about objects that hit the Earth. Throughout history, there's been a rain of comets and asteroids hitting the Earth and the Earth's accumulated material. But again, just in the last few decades, we have seen the opposite process, objects going up from the ground into orbit. And so life, and particularly intelligent life, brings about states of the world that would be impossible in any other way. Probably the deepest mystery of all, and I'll come back to this at the end, is how life got going in the first place. Nobody knows how life started. It's still deeply mysterious, but a very important philosophical and scientific question hinges on it. If life starts easily, we would expect it to be widespread in the universe. But if life on Earth is the result of some bizarre chemical fluke, some sequence of chemical reactions that are so unlikely they would happen only once, then we will be alone in the universe. So these are very important questions, and we really don't know how to answer them. Until recently, I'm going to tell you about some new ideas. I think that the puzzle of life was very well summed up by the physicist Max Delbruck in this quotation here. And I'll read this out slowly because I think every word here is important. And Delbruck is talking about how living things are made of the same atoms as non-living things, but when the atoms become incorporated into the living organism, then they seem to do almost magical things. So let me read this. It says, "The curiosity remains to grasp more clearly how the same matter, which in physics and in chemistry displays orderly and reproducible and relatively simple properties, arranges itself in the most astounding fashions as soon as it is drawn into the orbit of the living organism. The closer one looks at these performances of matter in living organisms, the more impressive the show becomes." And here we get to the punchline, as we say, "The meanest living thing becomes a magic puzzle box full of elaborate and changing molecules." Magic puzzle box, isn't that a wonderful expression? What Delbruck is really saying is that at the level of atoms, it's just known physics. We understand atoms, we understand molecules. But at the level of a living cell, it looks like magic. So how does magic come out of physics? How does magic come out of atoms? That's the problem I'm addressing. Now, 75 years ago this year, a famous book was published by Erwin Schrödinger. Now, Schrödinger was a giant of theoretical physics. It was he who was the co-architect of quantum mechanics. I'm sure you've all heard about quantum mechanics. It's the most successful scientific theory we have. At a stroke, quantum mechanics explains matter all the way from subatomic particles right up to stars. And so this is a very, very powerful theory that was developed by Schrödinger and others around about the late 1920s. And Schrödinger wrote this book, well, the book was published in 1944, based on lectures he gave in 1943. And that was, of course, in the middle of the most terrible war that this planet has ever seen. So what was Schrödinger doing? Well, he was Austrian, and he fled from the Nazis. And unlike many of his colleagues who went to work, say, on the Manhattan Project or other aspects of the Allied war effort, he decided instead to make a home in Ireland, in Dublin, and Ireland was neutral in World War II. Its president was a physicist, and he created a new institute, and Schrödinger spent several years in that institute, and I suppose, having been taken out of his natural environment, he felt that this would be a good time to explore something totally new. And in spite of the fact that Schrödinger was an undoubted genius, and that quantum mechanics is probably the most brilliant scientific theory ever, nevertheless, Schrödinger's brilliance could not explain life. He was still left with the feeling there's something deeply mysterious about life, and what he was interested to answer was whether physics can explain life. Now, when we say that, it seems easy to say, yes, of course, physics can explain life, but we have to be careful to distinguish known physics, what you might find in textbooks in a university library, from new physics, something that we have yet to uncover. So I don't think life is magic, really is magic, but I don't think it can be explained by known physics. I think we need new physics. And Schrödinger himself was very happy to leave open that possibility. He wrote in his book, "One must be prepared to find a new kind of physical law prevailing in it." And the point I want to make is not just a new law, but a new kind of law. And that's what I agree with. I'm going to tell you my ideas about what that new kind of law could be like. Now, part of the problem in approaching this issue of life, a problem for a physicist, is, physicists like to measure things. You say, well, what's the electric current flowing in a circuit? And we have devices that can measure that. Or what's the pressure in this room? We measure it, we could give a number. What we would really like, of course, is a life meter. We'd like something that would tell you that if it's below a certain level, that the system is non-living or dead. If it's above that level in the red region there, then it's living. Wouldn't that be great? We could tell if there is life present somewhere or not. NASA, the US Space Agency, would certainly like a life meter. Let me tell you about a moon of Saturn. It's called Enceladus. Now, I did promise the translators I wouldn't mention any strange names. All I can tell you is it's a moon. Here's a picture. It's a moon of Saturn, and it's pronounced Enceladus. And we had a lot of trouble in the early days trying to pronounce it. Some people called it enchilada. It sounded a bit like the Mexican food. But anyway, it's Enceladus. And what you see, the plumes of material spewing out of Enceladus, they were photographed by the Cassini spacecraft. There's another name, Cassini, Italian. And the surface of Enceladus has an icy crust. It's thick ice, but there are cracks in the ice, and this material is coming out. And the Cassini spacecraft measured organic material in those plumes. So the way this has been put to me by a friend of mine who works for NASA, his name is Chris McKay, it's almost as if Enceladus had put up a sign saying, life, free samples. And so could there be life? Could that organic material be the detritus of life that is existing below that icy crust? Well, one way to find out is to send a spacecraft there, and NASA is going to do that. They want to fly through that plume and sample that material and try to answer the question, is there life coming out of Enceladus? So they'd like a life meter to put, here look carefully, there you'll see the spacecraft flying through the plume. Is it possible to build a life meter? Well, the truth is that we have absolutely no idea how to define life, let alone build a life meter. And the very notion that somehow there are different degrees of life seems sort of absurd. Could we imagine a mission to Enceladus reporting back that in spite of 4.5 billion years of opportunity, Enceladus only got 38.7% of the way to life? That's a sort of meaningless thing. You feel, well, it's either got life or it hasn't. But we just don't know what quantity to measure that could distinguish between them. The real fundamental problem is not so much the lack of a threshold at which non-life turns into life. It's that the very concept of life seems to be very different from the way physicists like to describe the world. So if you ask a physicist what is life, you'll get an answer in terms of things like matter and force and energy and molecular shapes and so on. But if you go to a biology department and say, what is life? They like to talk about gene editing and instructions and translation and signals between different organs and different organisms. So they use the language of information. So we have the language, if you like, the physics language of hardware, of stuff, and the biological language of software or information. Any theory that tries to explain life in a common framework with physics has to incorporate information into it in a fundamental way. Now, life is invested in information in many ways. The most obvious way, and connecting with the theme of this year's festival, is that the universal genetic code, it's universal to all known life on Earth, we don't know about other planets, is the language of life. DNA, which contains the instruction, it's like the rule book for the organism, is famously written in a 4-letter alphabet, A, G, C, T. But the genes in the DNA code for proteins, and proteins are made out of 20 different types of amino acids, sometimes 21. So we've got a 4-letter alphabet encoding for a 20-letter product. So there has to be a genetic code that connects them, a mathematical code. And here it is. This is a table. The A, G, C's, and T's are the so-called nucleotides in DNA, the 4-letter alphabet of DNA, and you'll see the symbols there representing the amino acids which go to make up the proteins. There are 20 or 21 of those. And so this is a mathematical correspondence. There could be trillions upon trillions of different mathematical codes connecting these, but all life more or less uses the same code. So that's the language of life. It's a coded language. It's encrypted. So nature has encrypted the instructions for life in a universal mathematical code. But it doesn't stop there. DNA is used to transmit information horizontally from genes to proteins, and vertically as well, by inheritance. But in addition to that, genes don't act in isolation. They form complex networks, and information swirls around those networks, and you see one symbolically represented at the bottom left. But these networks that go to make up the information processing capabilities of cells, even the cells themselves exchange information. So even bacteria can form colonies that have different shapes and different properties by exchanging information. And when we get on to so-called higher or more complex organisms, like social insects, the information aspect of life becomes even more profound. So, for example, ants can engage in collective decision-making. No one ant has a strategy for the colony, but collectively they can make very smart decisions. We see it in the way birds flock. They exchange information, so they coordinate their activities. Perhaps the most striking example of information at work in biology is the development of the embryo. The information to build the embryo, which begins at this molecular stage, then is unveiled, it unfolds during the developmental phase, so that all the right bits are in the right place at the right time. An exquisite example of high fidelity information management and information control. And then we mustn't forget this thing up here in our heads. That is an information processing system of very great sophistication. And it doesn't really end there. We can follow the networks of information up to a planetary scale. This is a diagram produced by some of my colleagues at Arizona State University, and they've looked at how genes are organized on a planetary basis. And so I like to say that this was the original World Wide Web. Information is on a global scale in biology. And I'm not the only one to get carried away by the power of information to describe life. This is a quotation by Paul Davies. He was president of the Royal Society. He's a Nobel Prize-winning biologist. And in a paper called Life, Logic and Information, he had this visionary statement. And again, I'm going to read it out. I think it's very important. We need to describe the molecular interactions and biochemical transformations that take place in living organisms, and then translate these descriptions into the logic circuits that reveal how information is managed. This analysis should not be confined to the flow of information from gene to protein, but should also be applied to all functions operating in cells and organisms. So it'll be clear to you by now that information is a profound concept in physics and biology, and I think it's the glue that sticks together these two very different disciplines. Just like Newton provided the glue to connect the motion of objects on Earth with the motion in the heavens. So I should say a few words about what this thing information is. We use it in daily life in an informal way. We talk about the information in a bus timetable or something, but I'm using it as an abstract concept that can enter into the laws of physics. And the beginnings of what we now call information theory were laid down in the late 1940s by this man here, Claude Shannon, and he was given a very straightforward task. You'll be familiar if you try to talk to somebody down a noisy telephone line that you might be misunderstood. And so Shannon worked out a way of encoding information in such a way that it was most efficiently transmitted down a noisy channel. So how do you package the information so that the effect of the noise is least likely to garble the message? And it was he who defined the thing we call bit. You'll know about bits and bytes in computing. The bit stands for binary digit, and it's a very simple idea. This is the only piece of, not even mathematics, but arithmetic that I can show you. If you toss a coin, and I took the trouble to find Polish coins there, toss a coin, then it could come down heads, it could come down tails, so there are two possibilities. But when you look to see, then those two possibilities are reduced to one. So he defined information as reduction in uncertainty, just that. And it's possible to build a whole mathematical theory around that connects to information as it's used in physics and biology. So this now is a thoroughly understood part of engineering and science. But we're interested as to whether information can just be described, but can it actually have real physical effects? To use an English expression, can information have clout? Can it really make a difference? Can bits move matter? That's putting it most dramatically. The first glimmerings of an answer to that question came in the middle of the 19th century in a famous letter that the physicist James Clerk Maxwell, and again the translators should note that his middle name, Clark, would be pronounced by Americans Clerk. It's got an E, but it's Clark is the British, well in his case it was Scottish pronunciation. And he had this idea that if you had a box of gas with the molecules rushing around chaotically, divided into two, like this by a screen, with a shutter mechanism and a little hole, and then if there was a being here, this little being, who could see individual molecules and measure their speeds, then this being that became known as Maxwell's demon could open the shutter when a fast molecule came this way, or when a slow molecule came that way, and then keep the shutter closed for the opposite effects. And so after a while, all the fast-moving molecules would be here on the left and the slow ones on the right. Now, because molecular speed is a measure of temperature, it means the left-hand side will become hotter than the right-hand side. And any engineer will tell you if you have two boxes with different temperatures, you can run a heat engine and do work, like lift a weight or something, based on that. So what Maxwell was saying is that this clever demon would be able to use knowledge about the molecular motions to create a perpetual motion machine, to turn heat into work without doing anything else. And that violates a cherished law of physics called the second law of thermodynamics. I promised I'd come back to that. And roughly speaking, it just says that heat flows from hot to cold. We wouldn't expect to put a snow person, I think you would have to describe it these days, next to a fire, only to have the snow person grow bigger and bigger and the fire get cooler and cooler. So the heat flows in that direction. That's the second law of thermodynamics. Maxwell seemed to be saying that in principle it would be possible to make heat flow the other way, from cold to hot. Now you might be thinking, well, hold on, isn't that what a refrigerator does? And indeed, this is my refrigerator in Phoenix, and true to American style, it's a huge refrigerator, and it sits right next to an oven. You think, well, there's no logic in that, but that's the American way. And of course, what the refrigerator does, it takes heat from inside, the cool interior, and pumps it out into the kitchen. So it's sort of going in the opposite direction. But, of course, I have to pay an electricity bill to run that refrigerator. So there's a cost involved, a financial cost and a thermodynamic cost. And when you add that cost into it, this isn't any perpetual motion. Whatever work that the refrigerator could do has to be paid for by the work required to make the electricity. So everything comes out in the wash, again, as we say in an English expression. I don't know if that translates. Now, the point being that electricity pays for this system to pump heat from cold to hot. Maxwell said, you don't need electricity, information can do it. The demon can use its information about the molecular motion to perform this trick, to do work. And so information then, when we think about it, must be a type of fuel. Just like electricity, information can serve as a fuel. And that means we could have an information engine which would run on information fuel without any electricity or any other thing. It could just run using information. Now, when Maxwell conjectured this back in the 1870s, it was just a thought experiment. And it's taken 150 years for his ideas to become part of practical engineering. But today, the field of nanotechnology has advanced so much that it's possible to build information engines. And there are many, many papers just in the last few years of people building real Maxwell demons. Of course, they're not little intelligent beings. They're some clever little nanotechnology information processor in order to turn heat into work in this manner against the second law of thermodynamics. My favorite is this one. It's an information-powered refrigerator. Back to that. That has been made by, I hesitate to pronounce his name. I think probably no better than the translators. I guess Jukka Pekola. Anyway, he's Finnish. So you really can use information as a fuel. Now, you might think this is surprising, but life understood this for billions of years. So life has its own demons, its own nanotechnology in the form of molecular motors, little molecular machines. Our cells are full of nanotechnology. They're full of Maxwell demons, chuntering away, gaining advantages by playing the margins of thermodynamics, playing this information thermodynamic game. The one, I don't have time to go into many examples, but the one I particularly like is called the voltage-gated ion channel. And I like it because it's what's making you think now. I hope you're thinking about what I'm saying, because it explains how signals travel down from neuron to neuron in the brain along the axons. And they do this by employing Maxwell demons. What happens is that the ion channels, they have a membrane, and these membranes, the axons have a membrane, and the membrane have these proteins that stick through them with a hole up the middle. Here it is. There's the hole. And there's a gate, just like Maxwell's demon had a shutter. There's a shutter for these things. And when the shutter is opened, sodium ions can flow one way or potassium ions the other. And that's how you get a nerve pulse travel down the axons. The demons sense that the pulse is coming, and they open the gate, and the ions go through. And they can do this with almost no expenditure of energy. And that leads to one of the most astounding things in biology. Our brains have the information processing capability of a megawatt supercomputer, a supercomputer that would require megawatts of energy and vast amounts of cooling to operate. But our brains do it with the equivalent of a small electric light bulb. They're so energy efficient. And this is part of the story that they are using Maxwell demons to produce that efficiency. Now, this is one example of gene expression, of genes, the information in genes being used to affect physical forces, in this case electrical forces. But I'd just like to tell you briefly about some amazing work I'm involved in which the opposite is true, where physical forces can affect gene expression. And I'm just going to briefly mention the work of Michael Levin at Tufts University in Massachusetts. Keep one eye on the clock here. He likes to work with a worm called a planaria worm. Here it is. These worms are very entertaining. They have a head and a tail, and if you chop them in half, the head grows a tail, and the tail grows a head. I don't know if we have any teachers here, high school teachers, but children love to play with these worms because you can chop them up and get more worms. So it's a wonderful thing to do. As an aside, I once asked Michael Levin, well, but do these worms also have sex? And he said, yes, they do, but they prefer to be chopped up. So there we go. If you chop them up, you get 2 worms in place of 1. And of course, that raises the interesting issue about how the tail bit knows to make a new head and how the head bit knows to make a new tail. But that's the least of the mysteries, because what Mike can do by chemically manipulating the electrical patterns around the wound, the cut. I say electrical patterns, let me just, for the physicists here, explain very clearly that living cells are like little electrical machines. They have a membrane potential, an electrical potential across the membrane of a few hundred millivolts, and that's critical to making the cells operate normally. They achieve that by pumping protons out into the exterior world. And so it's a really important part. So living cells are like little electrical machines. And that's, let me tell you another astounding thing. The membranes are so thin that even with less than a volt potential difference across them, the electric fields in the membranes are comparable to that during a thunderstorm when there's a breakdown and a discharge. So some amazing things you learn when you study biology. Anyway, he can manipulate the membrane potential around there, and then he can end up making 2-headed worms and 2-tailed worms. So in place of a head and a tail, you've got 2 tails and 2 heads. I asked him, are the 2-tailed ones really stupid compared to the 2-headed ones? He said, it doesn't seem to make much difference. Now, this is the really astounding fact, and I could scarcely believe it when he first told me. What happens if you chop up a 2-headed worm or a 2-tailed worm? You might expect that when you do that, they would restore their normal anatomy, their normal phenotype, as biologists would say. But that isn't true. If you chop up a 2-headed worm, it'll make 2 2-headed worms, and a 2-tailed worm will make 2 2-tailed worms. But they have identical DNA. A visitor from Mars would think these are 2 different species. They're the same species, the same DNA, but completely different phenotype, completely different anatomy. And so that shows that how an organism looks and behaves is not all in the genes. In this case, it has to do with electrical patterning. And so that raises a really interesting question. Where is the software, the information necessary for the fragments to build the whole organism? Where is that stored? Not in the genes, not in the instruction book of life. It can't be, because they've got identical genes. It's stored somewhere else. We're trying to figure out where, but it's probably distributed globally in some way. And this we can think of as bioelectric memory. So something about the electrical patterning is memorized from one chopped up generation to the next. And here's another very amusing fact. If you take one of these worms and chop the middle bit out, then you think, well, does the middle bit, does it know which end is the head and which end is the tail? How does it know that? And yes, mostly, if you chop the middle out, it'll grow a head at one end and a tail at the other end where it's supposed to. But Mike and his research team decided to send some middle bits of these worms to the space station and chop the middle bit out, and about 15% of them came back with two heads. So somehow these worms know that they're in zero gravity, and this induces them to make two-headed worms instead of normal worms. So lots of questions flow from this. Is there an electrical code to go alongside the genetic code? And how do these electrical patterns communicate with, talk to the chemical networks that control all of life's processes? I've already said, how is that information propagated from one generation to the next? But here is the great promise. Can we manipulate the electrical patterns to correct birth defects or to manage cancer? Because cancer tumors have a very different electrical patterning, or even grow entire new organisms. That's part of the technological promise. But for me, the interest is in the information. How is it stored? What form is it in? Is it analog or digital? The genetic code is digital. Perhaps this is analog. So the language of life, then, is far richer than the genetic code. And the term that biologists give to all of this extra consideration is epigenetics. And so this summarizes that epigenetic control can take place by chemical signaling or through physical forces. And these physical forces, I've told you, can be electrical or gravitational. They can also be mechanical. It turns out that if you press a cell or subject it to a shear stresses, that can affect gene expression as well. So physics and information processing connect in a very deep way through Maxwell's demon and the second law of thermodynamics. Information really makes a difference in the laws of physics, and here we see in real biology. Now, I'm just going to spend a few moments before wrapping this up on the problem of how did life begin. Just got a few minutes, I can do this. Darwin himself refused to be drawn. He gave us a wonderful account of how life evolved on Earth from simple microbes to the richness and complexity of the biosphere that we see today. But he said, it is mere rubbish thinking at present of the origin of life. One might as well think of the origin of matter. That's a wonderful quote, I love it. Interestingly, physicists now think they understand the origin of matter, but we don't understand the origin of life. And this deep mystery endured for many, many decades. Here's Francis Crick, who co-discovered the structure of DNA. He said in 1973 that life seems almost a miracle, so many other conditions necessary for it to get going. So life's origin has stumped, that means confused, even the most brilliant scientists, and continues to do so right up to the present day. There have been experiments, someone would ask me if I didn't mention this, the so-called Miller-Urey experiment of trying to make the building blocks of life in the lab. This is a famous experiment by Stanley Miller and Harold Urey. So again, those are names I'm using there, in 1952, just within a few weeks of Crick and Watson discovering the structure of DNA. And Miller sparked electricity through a mixture of common gases for a few days and found that they made the amino acids, some of them, the amino acids that are the building blocks of proteins, the thing I was talking about earlier. But really this hasn't gone much further. The idea that we could somehow cook up life in the lab by doing a more elaborate version of this really remains a distant hope, a distant dream. I think we're a very long way from it. But the real problem is not, can we mix up the right chemicals? Because with a big enough budget, we can surely do that. The real problem is this. It's the genetic code. It's not enough just to have those molecules. Somehow, the software has to be inserted into the hardware. So it's a bit like saying, I know how to make a computer. It's made of bits of silicon and bits of plastic and bits of copper, and one day we'll just put it all together. You know it won't work unless you go to a software engineer and say, please upload an operating system and all the necessary bells and whistles, as we say in English, the elaboration necessary to run a modern computer. So how can molecules write code? And it's not enough just to say that the letters are a coded information source. We know that information is useless unless it has meaning. And Claude Shannon was very clear that his information theory was just about the efficiency of encoding and information transmission. It said nothing about the meaning of the information. But if a gene is anything, it is an instruction for the cell to execute some operation, like build a protein. It has to mean something for the molecular system that interprets it. Just like when I converse with you using language, it has to mean something or I'm wasting my words. But if I talk to you in code, then that meaning is shut off. So life has got a code, but it has to encode meaningful information. We have no idea at this stage how to enshrine the idea of coded, meaningful information in the laws of physics. Not enough just to have a Maxwell demon playing the margins of thermodynamics. We need meaningful information embedded in the laws of physics in some way. So that really does mean, as Schrödinger said, a new kind of physical law. Not just any old law, but a very different kind of physical law that refers not just to the local situation, but to the whole of the cell or the organism. It's a global thing. When we talk about meaning, it's something that is relevant only to a community of people or a community of molecules that has an agenda. These are very, very difficult ideas, very far from the traditional notion of physics. So I think there is new physics that is needed in life. I think life is explained by physics, but we need new physics, and I think the information physics that I've been telling you about is the first step to creating this new physics. And what we're going to see, and if the young people here want to make a career in science, that just as the 20th century was dominated by the physics of the very small, particle physics, and the physics of the very large, cosmology, this century will be dominated by the physics of the very complex, and information will be the linking concept to bring it into this unified scheme. And the one thing that I've learned about applying information to biology is that it's boundless possibilities, that just as human language can be used to tell an unlimited number of stories, just because you have the language doesn't give you the narrative. It is limitless. So in the same way, in biology, the language of life leads to open-ended complexity and unbounded possibilities to innovate. So if we go to other worlds, we may well find very different forms of life based on the way in which information is encoded and the different possibilities are explored. And so it seems very fitting to end my lecture I began with the work of a famous alumnus of the Jagiellonian University. I'm going to finish with the words of another alumnus, perhaps not quite so famous as Nicholas Copernicus, the writer Stanislav Lem. And he said, good books tell the truth, even when they're about things that have never been and never will be. They're truthful in a different way. And I think that encapsulates the nature of information in life. It embodies a bigger truth than all of the organisms put together. We have to understand that deep truth to fully understand life and not just look at the particular organisms that we find here on Earth. We've got to think big. And at that point, I think I will stop and take questions. So thank you.
Thank you very much for this fascinating lecture. And yes, we will have a short question and answer session now.
Yes.
And I will first take this privilege to ask
Please
some
do.
questions myself. So first let me ask you as a physicist and a mathematician. So you said that to explain life, we will need new physics. So do you think that this new physics will require new mathematics?
I might have guessed you would ask me that question. Look, it's entirely likely. And let me give you a really good example, and there's already people working on this. I didn't go into the details about the new kind of physical law, but I do have some ideas. And one of these, it's sometimes called top-down causation. What it means is that in traditional laws of physics, what happens to a particle, say an atom, it depends on the forces acting in its immediate locality. We call this as a local theory. But in biology, I've been pointing out that the local links to the global. We need to have some way of connecting the system as a whole to the components. And now, if you try to write down a law of physics to do that, mathematically, it's very hard, because now we're used to the idea, if I could just get technical for a moment for your purpose, a Hamiltonian system might be completely defined by its initial conditions, but this is not a Hamiltonian system. This is a system in which because the Hamiltonian might change with time, but it won't change as a function of state. So what we want here is a dynamical law where what happens to a component depends on the global state of the system. And there's a mathematician in Japan who's tried to capture that. There's any physicists here, it's a bit similar to the Hartree-Fock approximation in atomic physics. So there's a bit of a precedent for this. But I think that what this mathematics will show is that there will be novel pathways to complexity, which will help explain matter. So far, we've only been able to do crude computer models to insert these ideas. We haven't actually written down any equations. That's what we'd really like. We'd like somebody or other's law, like Newton's laws, that would do exactly that. We're a long way from that. We just have some crude computer models.
Okay, thank you. Well, and do you think that there's actually a single language of life, or will we eventually need some translators?
Yeah, I think if we're talking about life on Earth, because it's so interconnected, I think there will be a single language. I should just say, in case people here read my earlier book, The Eerie Silence, but haven't I suggested there might be a shadow biosphere of alternative life from a second genesis right under our noses, and that may be the case. But whether there is or there isn't, if there is another form of life either here or elsewhere, it might well have a different language. But if we need, I pointed out that the biosphere is like the original World Wide Web. It's a network of information, and so that the language ought to be the same. But there's no fundamental law, I don't think, that the language has to be the one that we have. And the other thing I have been at pains to point out is it's not just the genetic code, it's all this electrical stuff, all this epigenetic stuff, and that's got its own language. And there I'm not so sure. It may be that the language of electrical patterning is different in plants and animals, so I have no idea. But the genetic language is the same.
So it raises a question, how about life beyond Earth? Would it be based on similar structures, similar information patterns, or?
Well, that's our hope. So, I mean, our hope is that even if the language itself is different, a language will be apparent. So just like people found a Rosetta Stone, you could tell, even if you haven't translated some ancient language, you can tell it is a language from its structure. So we're trying to come up with a definition of life based on informational motifs. I hope that word translates correctly into Polish, a motif. A little bit like a branding. So we think there may be fundamental informational motifs that we would find on Enceladus, on Mars, or wherever we go look for it, and that we need that software definition of life, because no point in going to Enceladus and say, oh yeah, we found amino acids or something like that. The hardware on its own is not going to be convincing, but if you look for the software patterns, then it doesn't matter what life elsewhere is made of. It may be made from different molecules completely, but if it's got the same logical structure and the same complexity of language, then we could dignify it with the term life.
Okay, and well, finally, let me ask you about cosmology. So we were talking about the origins of life, but the current cosmological model predicts a rather dark future for the matter and for the living matter. So.
Well, it depends who you talk to.
Okay.
So now you're right. We're living fairly close to the origin of the universe. It's only 13.8 billion years since the Big Bang, and could go on forever. Even if it doesn't go on forever, it could be for trillions and trillions of years. So here we are, this atypical time. Why are we living now? Well, the skies are ablaze with the light from stars, and we depend on that for our existence. Yes. But when the stars go out, and in the far future, when the second law of thermodynamics makes it harder and harder to actually gain any energy advantage, what will happen? And there's an entire subject, it's been a theological subject called eschatology. Don't know the Polish for eschatology, but that's the term. And there's a science of eschatology, the end of things. And I wrote a whole book myself called The Last 3 Minutes, all about the end. And we don't know, because opinions differ, if life is really just about information processing, then it really boils down to, is there enough free energy in the far future to process that information? Can you have an infinite amount of information processing even in a universe that's dying because of lack of energy sources? Freeman Dyson wrote a paper on this many years ago in which he claimed the answer is yes. People still argue over that. So that will get us into very technical territory, I think, if we continue that conversation.
Okay, thank you very much. I think we can now ask some questions from the audience. Have some questions from the audience.
Of course, yes.
Yes, and the questions
I've got the translation
Pytania
device,
można zadawać zarówno po polsku, jak i po angielsku.
Is it turned on? I can't hear anything.
Am I audible? When you showed the information building blocks.
I can't actually see where you are because of the
I'm
lights,
here.
Never mind. Carry on. Oh, hello. Yes.
When you showed the information building blocks of life, I immediately thought of an entirely parallel set of information building blocks, namely the information building blocks of matter. So you have the charmed, strange, up, down quarks, and you have quite a number of writings that I've seen, I don't know, over the past 20 years or so, suggesting that matter itself is really no more than information. Pray comment.
Not only can I comment, I wrote a whole book on it, dedicated to the person who championed this, John Wheeler, who coined the term "it from bit," that ultimately he said, when we investigate the world, it's always in terms of some sort of yes, no answer, questions that we ask of nature. And so he thought that our concepts like atoms and molecules and particles and forces and so on, these were all secondary concepts based on the fundamental notion of information. So information being at the core of physics, just like it's at the core of biology. And I sympathize greatly with that. The book I'm referring to is called The Goldilocks Enigma: Why is the Universe Just Right for Life? It's about where the laws of physics come from and what they are, and I dedicated it to John Wheeler. And if you would like to know more about my thinking about the parallel narratives in physics and in biology, then then you need to buy two books. You need to get The Goldilocks Enigma and my new book, The Demon in the Machine.
Okay, let's have another question. Well, I can barely see from the stage.
It's not easy, is it?
Yes.
See a hand
Okay.
waving somewhere.
First here.
Hello, and do you think it's possible that new kind of life could emerge on Earth under current conditions, let's say without our help?
Yeah, that's a really interesting question, and I've thought long and hard and run little conferences on that very topic, whether life could start de novo here on Earth today. And the standard answer that biologists will tell you is that once life got going on Earth, it changed the conditions. So the conditions in which life can flourish may be very different from the conditions under which life can originate. And so I've thought a bit about whether maybe life started on Mars but came to Earth in meteorites, that Earth is a better place for life to survive in the longer term, but Mars would have been a better environment for it to start. Could it really start here on Earth? I wouldn't rule it out. Part of the reason for that is there's some evidence that maybe life started very deep under the ground, perhaps 5 kilometers beneath the surface or under the seabed. And I don't think that the activity of life on the surface of the Earth has really changed those subsurface conditions very much. So I think it's not impossible that it could be starting again all around us. But even if that isn't the case, even if you require conditions on the very early Earth, it still could have and probably should have happened many times. If life, astrobiologists love to believe the universe is teeming with life. They don't know that because we don't know how life began. But if they're right, if it's easy to get going, it should have started many times. And we mustn't rule out the possibility that there is an alternative form of life right here on Earth, right under our noses, or even in our noses. The thing is, we wouldn't spot it because most life is just microbes, and you can't tell by looking what makes them tick. You have to dig inside to their biochemical innards to find out what's going on. And so we could be surrounded by truly alien microbes and not be aware of it.
Okay, we had one question in the back, I think.
So you are talking about new information-based physics. Would this new physics be more like a new, different approach to a known physics, like, for example, Hamiltonian mechanics and Laplacian mechanics are two sides of the same coin?
Yes.
Or would it be something more general, like Newtonian and Einstein gravity?
The way I think about it at the moment is that this new physics would start to become important when systems become sufficiently complex, that there could be a sort of threshold of complexity at which we would begin to see new effects. Now, if I can answer this in a technical way to make that clearer, in quantum mechanics, under normal conditions, the evolution is unitary. We talk about unitary evolution. I think that this type of global, local link I've been talking about would mean that there would be some non-unitary terms entering into the evolution equations for quantum systems. But these terms would depend on the complexity of the whole system. And in my book, I talk about a particular measure of complexity that people use more in trying to define consciousness. It has to do with the number of feedback loops and so on. So I'm trying to encourage some collaborators to do experiments where you get molecules which are sufficiently complex that we might begin to see these non-unitary effects, but still small enough to where you see quantum effects. So it would be the sort of quantum classical transition in this complexity, as well as the sort of non-living living. Now this is all pure speculation, but it does look like you could perform those experiments. You could try to look at molecules of greater and greater complexity and see if there are any sort of funny quantum effects going on. And there's a whole chapter of my new book on quantum biology, including one about the conduction properties of organic molecules, electrons tunneling through molecules. And I think it's entirely possible we'll find something there. There are surprising results that people don't fully understand, that we might find something that gives a clue. So I don't think it's going to affect what's going on at the level of atoms and simple molecules, because the terms in the equation would be too small. But when we get to that sort of threshold of complexity, molecular weight of, I don't know, 500 or something, I'm just making this up, that's where you might begin to see these non-linear effects creeping in. It's all conjecture.
Okay, let's see.
How do you relate to Rupert Sheldrake's theories, which seems to have some connection with what you're talking about?
Yes, so you're referring to Rupert Sheldrake. He's an old friend of mine who lives in London, and I've known him for many, many years, and we love to talk about these sorts of topics. And he falls into the category of people who I don't believe his theories, but I love to hear about them, and I think he would probably regard what I'm saying as supporting his general ideas, and I must acknowledge that over the years he's made me think about the world in a certain way, so I have some debt of gratitude to Rupert, but he wants a mechanism that can involve information patterning, but in disconnected systems. He would like it, something happens here in Krakow, for it to make a difference in London, and it's very hard for me to understand any sort of law of physics that could operate in that way. So I don't think that this is quite what Rupert Sheldrake wants from his so-called morphic resonance. That's how he describes it. Don't think it's the same.
In your new book, you mentioned also Jeremy England's work.
Yes.
I was wondering what you think of his, I think, 2016 paper that the second law of thermodynamics could explain how life arose in the first place. He made some pretty bold statements back then.
Yes. So you've touched on a vast subject. First of all, you mentioned the work of Jeremy England, spelt the same way as the country, and I know him fairly well, and he does some really interesting work trying to connect the laws of thermodynamics to what's going on in life. And I mentioned, you're quite right, briefly in the book, how he's able to estimate just how close life is coming to thermodynamic perfection. So I like that general line of reasoning. It's really hard to go far beyond what Jeremy England has already done because the systems just become so much more complicated. But I do feel that if we are, I've been making the case that something like a Maxwell demon is a work in living organisms, or at least in parts of living organisms, and that is fundamentally a thermodynamic concept. And what his work is doing, it's providing a way to measure just how demon-like a biological process is. And of course, some of them you know, they don't get right to the Maxwell-Demon limit, not right up to what Maxwell originally envisaged, but they get very close. And the one that I am most impressed by, and I'm grateful to Charles Bennett at IBM for drawing my attention to this, is the replication of DNA, that the replicase enzyme crawls along the DNA and then it makes a new strand and so on. And it does this almost reversibly, almost complete thermodynamic perfection there. Because if something is reversible, it's not not making any entropy at all. And so it's getting very close to that. And so life has really learned how to do these fundamental processes very inexpensively if we're talking about entropy generation rather than money. Life is really clever at using these sort of Maxwell-Demon type processes. So I hope that answers your question.
The first thing is that I want to thank you for this beautiful lecture, because after that I can feel that everything is just one, because the lecture get this impression. And the second thing is that I was wondering about that. You said that information is something that changes the matter, and we as human beings and also as electrical machines at the same time can change the matter. And as we sitting here, we are changing the matter actually by our consciousness.
Yes.
And there was, I also remind an experiment that was, I think, in Berkeley, but I don't remember the scientist. And the experiment, it was just people were sitting and watching little balls, and these balls were just going to the left or to the right. And
I think this was Helmut Schmidt at the University of Texas at Austin, if I remember, about 30 years ago.
yeah, and they were just thinking if they want the balls to the left or to the right, and they were actually goes there where they wanted to go.
Well, we're back to Rupert Sheldrake again, I think. So this falls into the category of what people sometimes call the paranormal. And I'm a skeptic about the paranormal, as you might expect. I'm a physicist. I would love to believe that people can move electrons with the power of thought alone, even if they're not connected to them. I'm very aware of those experiments. People who work in paranormal phenomena usually say, well, the difficulty is these effects are very small, so it makes sense to then look at quantum systems where the slightest influence might make a difference. And so that was the motivation behind the experiments you mentioned. I have yet to be convinced that this is statistically significant. Richard Feynman was very good on this topic. He said that with good science, the more precisely you do the measurements, the better the claimed effect is demonstrated. With bad science, the more closely you do the experiments, the worse it gets. And I think some of these paranormal phenomena fall into that category. If you're a bit sloppy with your protocol, you seem to get a very big effect. And then you think, oh, we must tighten up, and the effect gets smaller, but it's still there, and then you tighten up more, and it shrinks and it shrinks. And I have a horrible feeling it would just shrink to zero if you did it properly. But I have to be open-minded. I'm a scientist, and I would love to believe that something like this has a basis in fact. And who knows, maybe it does. And maybe what I've been talking about will be a little window into that world that up until now people have dismissed. I hope that's the case, but I can't be honest with you and say that I'm convinced of that now.
I also have a question. You certainly, I'm here.
Where are you? Where?
You certainly heard about this concept of Roger Penrose,
yes.
that we need to understand this gap between classical physics and quantum physics
Yes.
to understand how consciousness works.
Yes.
And that these microtubules may be involved into creating somehow consciousness. What do you think about it? And do you think that that these microtubules may be also involved into creating the software for translating the genetic code?
Thank you for that question. You won't be surprised that there is a chapter of the book on consciousness. It's called The Ghost in the Machine, and there's a section on Roger Penrose's work there. I know Roger very, very well. We're in contact with each other almost every month. I've known him all my career, and I have known him through the genesis of this set of ideas. I also know Stuart Hameroff very well because he's just down the road at the University of Arizona in Tucson. I work at Arizona State University in Phoenix. So I know the two key players, and my answer is very much like the answer to the previous question, which is that I love hearing about all this stuff, but I'm very skeptical that there really are quantum effects going on at the level of microtubules. I don't rule it out, but the evidence I've seen so far makes me really very skeptical. So we need to do more work, and Roger himself is planning some more experiments. He has my full support because stranger things have happened. There was a time when people said you couldn't have superconductivity above a few degrees Kelvin, and now we have superconductivity at liquid nitrogen temperatures. Nobody expected that. So in the quantum world, we can find that there can be amazing surprises. But I remain to be convinced by that particular set of ideas.
Okay, let's have maybe 3 more questions.
Thank you. I have a slightly philosophical question, a little bit more like a common folk question. I just came out to this universe, had no idea of its existence before, so I'm, pedestrian coming in a little bit into this. So the question relates to effort scale. So you said that a little bit to the Rosetta Stone and to the coming into the complexity era of science and scientific experiments and understanding. Do you think that the amount of possible future efforts describing the scale of how to understand the concept of life that you just unfold here would be similar to trying to understand the concept of human nature by reading all the possible books that are in there written down by human? Like, do you think that discovering the language, if it is really there to be discovered, will lead us to a similar future effort of like endless reading into what life really is?
So that's an interesting question. In my own mind, I see human nature as much more difficult and complex than, for example, the information encoded in DNA. I think we can elucidate the laws of life, even if we have very little idea of, we might say, the laws of human nature. I think the brain is so complex. Humans have to be seen in the context of their whole society, not just in isolation. And I think that's really very, very subtle. I think it'll be a long time before, if ever, before we have a complete understanding of what it means to be human and to be part of a community of sentient beings. I think it's a really, really tough thing. But I'm hoping that we might solve the problem of information and life within the next, say, 2 decades, to the point where we really could give NASA that life meter and they could send it off somewhere and to look for life based on its informational qualities. I think we would be a very long time in the future before we could have, so to speak, a mind meter that could be flown off into space and it would report back that there's consciousness on some planet. That seems very far-fetched to me. I know in science fiction they do that, but I think detecting life as opposed to detecting consciousness. We might detect intelligence through technology, but that's not the same as consciousness. So human nature, I think, is a very tough one.
Okay, do we have any other question? One over there.
Okay, so you mentioned our great author and futurologist Stanisław Lem, and I would like to also relate to that because he written a book, Golem, and in this book the humanity built a super complex supercomputer called Golem, and he's telling the humanity like his predictions for the future and his opinion on this the current situation. And he said something like, evolution is a dead end. It goes nowhere because it's just about transforming information. And the first like biological machines were perfect because, you know, the first like plants. Plants are just, you know, transforming sun into their own energy. And the first algae, first bacteria, probably did something similar, just transformed sun to their own food. And we are more complex as people, but it's less perfect. Do you think that evolution is a dead end and we are going nowhere?
You've really asked two questions in one there. At the end of my talk, I pointed out that one of the characteristics of life is, in fact, the open-ended, limitless possibilities. That we can think of evolution as exploring a possibility space, and it sampled a tiny, tiny, tiny fraction of all the possibilities that are out there. So no, I think the evolutionary process has the ability to produce, as Darwin said, forms most wonderful, which are almost beyond imagination. But there was another aspect to your question, which I've now forgotten, I'm afraid, which I was going to say something different. So you said, is there something more efficient that we can do? Was that right? Could you just repeat the last part of the question? Your last sentence. What?
Because the first organisms were more perfect, more efficient, because they transferred directly the energy of sun into.
So you mean the complexity of?
Yes, because now we are more complex. We have brains, we have hands, but we're less perfect, less efficient in.
Well, it's true that from a strictly thermodynamic point of view, we're very expensive. That's right, although still remarkably efficient, as I've already pointed out. But it depends what your vision is. If your vision of the future is to just have for things to get better and better rather than worse and worse, to go against the second law of thermodynamics, then there is still, for the next trillion years or so, still plenty of free energy to drive these more complex, less efficient thermodynamic processes. And so, apart from the very far future of the universe, which I mentioned earlier, I don't see this as an impediment. I think there's plenty of energy to go around, and that we could imagine a future with much greater complexity and many more wonders, biological and non-biological.
Okay, I'm afraid that we have to conclude here.
That is it.
But,
got to go and sign books, haven't I?
Professor Davies will still be here for a few minutes signing the books. So let's thank the speaker once again.